Remember, to find the domain of a rational function, you are careful about the denominator and you are trying to make sure that the denominator is not equal to 0. In order to accomplish that, we would rather force the denominator to be equal to 0. So I'll write down x squared minus 36 equal to 0. And then essentially we're going to solve it for the values of x. If you remember, I call them bad points. So I will go ahead and add 36 on both sides, and I will get x squared is equal to 36. Then I take the square roots of x squared on both sides. And left hand side, as you can recall, is absolute value of x, which is equal to 6. So I get two solutions. One is positive 6 and the other is negative 6. So those are my two bad points. Then I'm going to go ahead and draw my number line and plot my 2 points, which I have called the bad points. Both of them, 6 and negative 6, are bad points. So I'm going to plot these 2 points on the number line, and then I will tell myself I'm not allowed to take this bad point, I'm not allowed to take this bad point, and I will take everything else in the domain. So then interval notation of the domain, that's how we will write every single domain. We will use the interval notation and we will say it's negative infinity to negative 6, union negative 6 to positive 6, union 6 to infinity. And that would answer my question. And this is essentially the way to solve any problem when asked to find the domain of the rational function. The next thing, of course, it is asking us to find all real values of x such that the equation fx is equal to 0. As you can imagine, if you are trying to find out fx equal to 0, it essentially means you are trying to find out y equal to 0. So we are trying to find out the x-intercepts. So we talked about finding x-intercepts for a rational function. We're just going to do that separately in this problem. Last time when we were drawing the graph, we did all these steps. I'm going to just do it separately for each individual problem. Now this problem is a little different. As you can recall, I said in order to solve for x-intercepts, you need only one rational expression. And I have two of them here. I have negative 20 over x plus 16 plus 11 over x plus 13, which recalls the fact that I need a common denominator. What does that mean? It means you write down both of these rational expressions, negative 20 over x plus 16 plus separately write down 11 over x plus 13. And then in order to make sure that I have the common denominator, I'm going to multiply the denominator factor on x plus 13, 11 over x plus 13, to both top and bottom of the first rational expression. So multiply x plus 13 with negative 20 and multiply x plus 13 with x plus 16. Similarly, the other denominator factor, x plus 16, will be multiplied with the top and bottom of the second rational expression. So multiply x plus 16 with 11 and multiply x plus 16 with x plus 13. And then, as you can imagine, I'm going to combine these terms, but before I do so, I need a little bit of distribution and simplification. So negative 20x, and then I do multiply negative 20 with 13, and I get minus 260. And this is over x plus 16 times x plus 13. The one thing I will remind you over and over is never simplify the denominator. There is a reason why we will not ever simplify the denominator. The numerator is other way around. We actually need to simplify it, and if it is not factored, then we are going to factor. The denominator, it's already factored. We're not going to bother about it. So let's carry on. Now we're going to distribute 11 over x, so you get 11x, and then 11 times 16. And when I do 11 times 16, I get 11 times 6 is 66, 6 carries on, 11 times 1 plus 6 is 17. So 176 over x plus 13 times x plus 16. What it has done for us, it has given us the same denominator in both rational expressions. That's what we wanted. So now we can combine them. Instead of writing two rational expressions, we're going to write only one of them, x plus 16 times x plus 13. And on the top, I'm going to write down all the terms I have from either expression. So minus 20x minus 260 plus 11x plus 176. And then I'm going to combine the terms. So negative 20x plus 11x is going to be minus 9x. These are the similar terms. And then you have minus 260 and 176. And when I combine them, I get negative 84. All over x plus 16 times x plus 13. And I don't have to follow any particular pattern when I'm writing these factors. I can say x plus 16 times x plus 13, or I can say x plus 13 over x plus 16. In your problem, they don't contribute in anything. What next? Again, I want you to remember when you say a fraction is equal to 0, because you're solving for fx equal to 0. So when you say a fraction is equal to 0, I'm only concerned about the numerator. The numerator is now equal to 0. So I'm going to go ahead and say minus 9x minus 84 equal to 0, and then solve for this linear equation. So you add 84 on both sides, you get minus 9x equal to 84, and then you divide both sides by negative 9. So I get x by itself equal to negative 84 over 9, which, if you recall, I can divide both top and bottom by 3, and if I do so, I get on the top 28 and on the bottom a 3, and this is dividing both top and bottom by 3. So this one looks like the x-intercept. The only other thing I have to make sure that whatever solution I got for my x-intercept is not a bad point. How do I make sure of that? So what are your bad points in this solution? The bad points in this rational expression are going to come from the bottom, the way we found the denominator. So one of them is going to come from x plus 16. You set it equal to 0, you get x equal to negative 16. And we're going to not say that negative 16 is equal to negative 23. They're not 28 over 3. So these two things are not equal to each other. So this is good so far. What is the other bad point? It's going to come from x plus 13 equal to 0. You solve for x, you get x equal to negative 13. And again, see, negative 13 is not equal to the solution we got. So I will say that indeed this is the solution. So I wanted to know all real values for which fx is equal to 0, and I found out there is only one, and that is negative 28 over 3. So whenever I ask you to find x-intercept for a rational function, this is your adaptation. This is what you are going to use in order to understand the x-intercepts of rational function. The next problem, of course, as we can see, it's talking about b being a constant. I want to understand fx when b is given as follows. So what it says, if f of b is large, then 1 of f of b is what? So if you have a large number, and if you have a non-zero large number, then 1 over f of b is going to be a very small number. So I will say f of b is large, then 1 over f of b is small. But remember what I said as well, provided f of b is not equal to 0. This is one thing in rational function we're going to be careful all the time. The denominator can never be equal to 0. Similarly, if f of b is small, then 1 over b, f of b is large. And again, I'm going to remind myself, provided f of b is not equal to 0. If f of b is equal to 0, then what? Then 1 over f of b is not defined. That's where you are going to talk about the bad points. If f of b is equal to 0, then 1 over f of b is not defined. The idea behind working these out is going and to talk about the vertical asymptote. So we have a couple more. If f of b is positive, then 1 over f of b is also positive. because 1 is already positive, and if you divide by a positive number, it remains positive. But again, I will say provided f of b is not equal to 0, which is redundant in this expression because I'm saying f of b is positive, so I don't have to worry about f of b not being equal to 0. But I will still go ahead and say that so that we remember. If f of b is negative, then 1 over f of b is negative. And then I know that negative means it is not equal to 0, but it doesn't hurt if I go ahead and say that if f of b is not equal to 0. So let's do one more solution, and this one is a little more intricate because you have a bunch of n terms, so the variable is n in this problem, but the process of solving it is not at all different. So what I need to do, as you can recall when I was solving the first rational expression in the previous page, I said the denominators need to be factored. And once it is factored, we don't simplify. So on n over n plus 2, I don't have to do anything. On 1 over n minus 3, I don't have to do anything. But n squared minus n minus 6, I'm going to go ahead and factor. So I say n squared minus n minus 6. And then you recall the coefficient of n squared is 1. The constant term is negative 6. So I multiply them. 1 times negative 6 will give you a negative 6. And you are going to tell me two numbers so that I multiply those two numbers, I get negative 6. And I add them, I get a negative 1. Why negative 1? Because the coefficient of the middle term is negative 1 there. That's the process of factoring. So recall, if you multiply negative 3 and 2, you get negative 6. And if you add them, you get a negative 1. So what I get to say? I get to say n squared minus 3n because of this minus 3 plus 2n because of this plus 2 minus 6. Then out of the first pair of terms, you can factor out n and you will be left with n minus 3. Then from the second two terms, you can factor out a positive 2. Remember, I have to factor out this sign. If I take out positive 2, I get n minus 3 as well. So this is my common group of terms, which I will now factor out. And I will get n minus 3 times n plus 2. So I have factored the denominator. So let's go back to our original problem. Now I will say it's n over n plus 2 plus 1 over n minus 3 equal to 4 minus 3n. And instead of writing down n squared minus n minus 6, I will write down n minus 3 times n plus 2. This is what I wanted. I wanted the quadratic denominator to become a factored linear form. On the left-hand side of this expression, you will be needing common denominator because I have more than one expression. So what I do, I look at the first expression and I see that the denominator is n plus 2. Whereas in the second one, the denominator is n minus 3. So take that, multiply with top and bottom on the first one. Similarly, you look at the second one, the denominator is n minus 3, but the first one is n plus 2. So go ahead and multiply the top of the second one by n plus 2 and the bottom of the second one by n plus 2. And recall, these are all distributions. So if it helps, put on parentheses around the multipliers. That will help you remember to distribute. And so we will start simplifying. I will get n squared minus 3n over, remember it's n plus 2 times n minus 3, and I do not do anything with the bottom. Whereas this one is 1 times n, so I will get n plus 1 times 2 is 2 all over n minus 3 times n plus 2. That's your left-hand side. Right-hand side, absolutely no work needed here. So I'll just go ahead and say 4 minus 3n over n minus 3 times n plus 2. Now on the left hand side I can combine terms. I will get n squared minus 3n plus n plus 2. These are the terms at the top. Bottom, I will just write one of them, the common denominator, n plus 2 times n minus 3. And set it equal to the right hand side, 4 minus 3n over n minus 3 times n plus 2. Now, if you look a little closely to the two expressions on the two sides, you will see both of them has n minus 3 on the bottom. So what I do? Cancel them. Both of them has n plus 2 on the bottom. What I do? I cancel it. And what is the upside of doing it? You have only a quadratic expression on the left hand side and a linear expression on the right hand side. Hence, we're going to get a quadratic equation. So what I do now? I go ahead and say that the left hand side is n squared. Now see, you have negative 3n plus n, which is a negative 2n. And then you have a plus 2, that's the left hand side, should be equal to the right hand side, and that's 4 minus 3n. Again, remind yourself, the denominators are gone. I don't have to worry about them. Now this one, you know, to solve, I need all terms on one side. So I subtract 4, I add 3n so that the right hand side is equal to 0. So if I do so, I'm going to end up having n squared plus n. Plus 2 minus 4 is a negative 2. And this side, everything is cancelled and you are at 0. So in order to solve that, I need factoring one more time. So I will say 1 times n squared. So 1 and negative 2 multiplied will give me negative 2. I need two numbers that multiplies to negative 2 but adds to a positive 1, coefficient of the middle term. And clearly these numbers are 2 and negative 1. So I go ahead and say that this is n squared plus 2n minus 1n minus 2 equal to 0. From the first two, factor out n, you get n plus 2. From the second two, you have to factor out this minus, and all you can do is one more. And you are ending up with n plus 2 again. So now n plus 2 is the common group of terms, which I'm going to factor out. If I do so, I get n plus 2 times n minus 1 equal to 0. Well, now I know how to solve this thing. I will go ahead and say that hence n is equal to negative 2. That's coming from the first factor. Or n is equal to positive 1 coming from the second factor. Am I done? No, because I did not talk about the bad points yet. Well, what are the bad points? If you look at both denominators, they are exactly the same. Remember how I canceled all of that? So what are the bad points? One of the bad points is going to come from this term n plus 2. So n plus 2 is equal to 0, means n equal to negative 2 is a bad point. What else? The other one is going to come from n minus 3. N minus 3 equal to 0, which will mean n equal to 3 is a bad point. And also remember, I told you already, I don't have to worry about this side anymore because the two bad points I get from this are exactly equal to negative 2 and 3. We have seen that they have the same factors. So now see, 3 and negative 2 are bad points, but negative 2 is one of your solutions as well. Solution cannot be a bad point. So what I do? I say, even if I found negative 2 as a solution, that is not accepted as it is bad. And I say the only solution or the x-intercept is n equal to 1 for my solution. So it's a little intricate, a long problem as you can imagine, but all the processes we have involved in solving this thing has come from something we have done in our class. So try to practice this solving rational equations. Okay, so we're going to go ahead and talk about vertical asymptote. So what I'm going to do, I'm going to skip this picture you are seeing. That's the formal definition of vertical asymptote, which we talked about last time in class. And straight ahead, start solving problems at page number 3. So example 5 is asking me to find the vertical asymptotes, if any, of the graph of each rational function. The first one is fx equal to x over x plus 4. So recall the process. Simplify. That's your first step. Simplify means if you have other than linear factors, which in this problem I don't. See, this is a linear term. X plus 4 is a linear term. So I don't have to simplify anything. So that tells me, go ahead, set your denominator equal to 0. and you get x equal to negative 4. And what is that? This is the vertical asymptote. I go to my next problem and see this time these are not simplified. Why? Because I see x on the top, I see x on the bottom. That can be cancelled because it is the same factor. So what I do, I go ahead and cancel the factors and rewrite this as 1 over x plus 4. And then I start to write down the vertical asymptote by solving the denominator. So I say x plus 4 equal to 0. So x equal to negative 4 is my vertical asymptote. So both problems, I have the same set of vertical asymptote, even though I have different rational functions. The other thing we will do is finding vertical asymptotes and intercepts together, which is our next problem. So it's asking you find all zeros and vertical asymptote. So we'll start solving the problem by finding the zeros. How do I solve it for zeros or solution? I set the rational expression equal to 0. Remember, it means there is only one thing I need to recall, that the top is equal to 0. Forget about the bottom for the time being. Set the top equal to 0. Start solving. So you add 1 on both sides. You get x squared equal to 1. Then as we recall, we will take square roots and I will get absolute value of x equal to 1, which has two solutions, x equal to 1 and x equal to negative 1. So the zeros are 1 and negative 1. In set notation, we will write set of 1 comma negative 1. Those are zeros. So if I have asked for zeros, this is how you are going to answer. But if I ask for x-intercept, then you know that we answer in a certain different way. We say that 1 comma 0 and negative 1 comma 0 are the two x-intercepts. Then I'm going to talk about vertical asymptote. Well, in order to talk about vertical asymptote, I'm going to set the denominator equal to 0 because I need to know the bad points as well. So I will subtract 1 from both sides. I will get x squared equal to negative 1. Take the square roots on both sides. I get absolute value of x equal to square root of negative 1. And then remember, this is not a real number. And whenever we encounter the situation, square root of negative 1 is not a real number, we say that there is no solution. What does this mean? This means, number one, there is no bad point. This is one such rational function where there is no bad point. So both of your solutions or x-intercepts are good. Both of them are good because I would discard if they're bad, but none of them are bad. What is the second thing I learned? There is no vertical asymptote as well. Because vertical asymptotes are going to be bad points. So there is no vertical asymptote as well. Would answer my question? So we have learned that there are rational functions where there is no vertical asymptote. It is possible. We're going to associate the concept of vertical asymptote and horizontal asymptote all together with long-run behavior. And all of these pictures and the rules we have talked about last time in class. In fact, if you go to shared class file, one of our friends from class has taken the picture of the board and I posted it on shared class file under completed lecture notes. You can get all the things that I have talked about last time in class from there. So let's talk about horizontal asymptotes separately. Remember, the two information you need is degree of the top and degree of the bottom, and then compare them. So degree of the top on the first example is 1, because it's x to the power 1 here, whereas degree of the bottom is 2, that's here. So if I call n the degree of the top and m the degree of the bottom, I will say n is 1 and m is 2. So what is that relationship? Degree of the top being 1 is less than degree of the bottom. And then if you recall the rules, it says if degree of the top is less than degree of the bottom, then y equal to 0 or the x-intercept or the x-axis is the horizontal asymptote. So I will say that horizontal asymptote is given by y equal to 0. The straight line, the x-axis, or y equal to 0. The next example, the degree of the top. So say n is degree of top, and if you recall, it is 1 as well, whereas on the bottom, which is, I'm calling it m for no reason, degree of the bottom is m, and that is 1 as well. So degree of the top is equal to degree of the bottom. That's our second rule. Degree of the top being equal to degree of the bottom, I get to say y equal to leading coefficient of top over leading coefficient of bottom is going to be the horizontal asymptote. So what is the leading coefficient of the top? The leading coefficient of the top is -5, and leading coefficient of the bottom is 7. So I get to say that -5 over 7. Hence, y equal to -5 over 7. This straight line is the horizontal asymptote. Would answer my question on this one? And let's see how we can combine all this information together now. So for the next example, I can just find out what are the vertical asymptote and the horizontal asymptote and try to answer the question that way, or I can use our old trend transformation. So see, I have given you the graph of fx equal to 1 over x. That looks like this thing. Those are the two branches for fx equal to 1 over x. And you can think of the graph of fx equal to 1 over x squared, where the branches are this way. Both of them are over the y-axis. If you recall these two graphs as your parent functions, then what you can do, you can use them and transformation in order to understand the graph of the next function. So see, when I say 1 over x plus 7, this is a shift to the left by 7 units. Whereas this one is a shift downwards by 6 units. So together these two, remember the function I'm talking about is fx equal to 1 over x. If I shift it down by 6 units and left by 7 units, then I get this one. So fx equal to 1 over x is this nice shape. What you are going to do, shift it 7 units to the left. So when I shift it 7 units to the left, I'm looking at something like this. And then I'm going to shift it down by 6 units. So shifting it down by 6 units, I will get this branch will come down here, and then the other branch will be somewhere here. So that's this one. So I'm looking for this picture, and as you can recall, the picture number C is looking like the one that I have. It has shifted 7 units to the left, and it has shifted 6 units downwards. So that's your right picture. And see, I did not use any concept of intercepts or anything or finding the asymptotes. I just used simple shifting transformation from test 1 period to answer this question. So we'll go to page number 6. In page number 6, we're going to talk about the 7-step process that we started working on our problem last time in class. If you include all these information, you will get done with the graph of the rational function. So let's talk about the number line test in step number 6 from last time's class. So we're going to talk about two different notation. If I say x goes to 8 and then in the power I write plus, it means x goes to 8 from right. And this expression means it is talking about what is the sign of the infinity. Remember, these are vertical asymptotes. So either I grow up without any bound or I grow decay without any bound. So this or that. Which one is happening? Well, we will do number line test and understand that. It's actually pretty simple. Whereas if I say x goes to 8 to the power minus, that means x goes to 8 from left. So I want to understand the behavior of the vertical asymptote. So it's as simple as a number line test. Your vertical asymptote is at 8. Take a point on the left, take a point on the right of 8. So let's say I have taken the point 7.5 on the left and 8.5 on the right. What I do? I put them in my function 1 minus x over x minus 8 whole to the power 2. That's the function. I'm going to test the points 7.5. So what do you get? You get 1 minus 7.5 over 1 minus 7.5 whole to the power 2. I should have said 7.5 minus 8. I'm so sorry. So this is 7.5 minus 8 because I'm replacing the x by 7.5. And then you have a square. So if you look at the top, the sign of the top is a negative number. Whereas the bottom is a negative number, but then I have squared it. So I get negative over positive, which is altogether negative. So the sign here is negative. What does that mean? Means your graph is decaying without any bound. It is going towards the maximum negativity. So I go ahead and say that on the left hand side, the graph goes to negative infinity. So what is the left hand side? Remember, this is going from right. This is going from left. So I said that, then this function goes to negative infinity as your x goes to 8 from the left hand side. We'll talk about the right hand side now. For the right hand side, I pretty much do the same work, except this time I put in 8.5 for my x. So I get 1 minus 8.5 on the top, 8.5 minus 8 on the bottom, and then I squared it. The top is still a negative number, so negative on top. The bottom is positive, and then I squared it. Doesn't change anything, so I still get negative over positive, which essentially is a negative number. So this is also negative. And what I know, that the graph will fall down without any bound towards the maximum negativity. Hence, even on the right hand side, I will say the function goes to negative infinity. And we were doing this thing while we were drawing the graph. I just wanted to do it separately before we start solving questions of this type a lot. So let's go to page number 9. So page number 9 has given you 4 graphs versus 4 functions, and it wants you to find out which function associates to which graph. So see, I have the function 1 over x. On number 3, you have the function 1 over x. That's easier to find. So a graph is like this. So I will go and find it, and I will see that it's number 2. So the graph number 2, I will say associated with function number 3. Then you see negative 1 over x. Number 2, you have negative 1 over x. So if this is 1 over x, what will be negative 1 over x? You are flipping them around the x-axis. It's a reflection along x-axis. How do I understand that? Well, this branch is going to be under here because you were taking a reflection. This branch will go over x-axis, so I will get a branch over here. Which one is this graph? Well, as you can see, it is the third one. This is your, actually, you know what? These are numbered A, B, C, so I'm going to just use them. So graph number C is associated with the negative 1 over x. So let's go ahead and do it. Instead of saying it 2, I'm just going to call it B. And I'm going to call negative 1 over x as my graph C. Then I do 1 over x squared. 1 over x squared is also a parent graph. And 1 over x squared is pretty simple to remember. You think about 1 over x, which is this branch and this branch, except having the negative branch over here, you take it upstairs. So this one stays, and this one is your new one, except having it here, you put it on the positive y-axis. So which one is this graph? Well, it is A. The graph number A is your option. So I'm going to go ahead and say that this is A, whereas negative 1 over x squared, you can find it in pretty similar way. It is a reflection along the x-axis, so I will instead get this branch and I will get this branch, and I will say that that's the only one left, and it's number D. So that answers my quest for transformation and understanding reflections and rational functions graph. So the final thing is using the 7-step process in order to identify graphs of rational function. And if you recall, we have solved the problem already last time in class, and I am planning to go over example number 14, which is also using the 7-step process to solve for the graph of this rational function. So I will do it, and if you have to go, then please go ahead and go. I'm going to still work on this problem. As I said, I'm recording this session. As soon as I'm done, I'm going to send it to you. If you are willing to stay, then stay. If you have any question about the things that we have talked about so far, please email me or text me through Skype. As soon as I'm done with the session, I'm going to start answering your questions. So for this problem, we're going to first talk about the domain. That's the first step of the 7-step process. And I will just set the denominator x squared minus 9 equal to 0. Remember, it is better to factor this thing in order to know the 2 points where this function is going to be bad. So I will add 9. If I don't want to factor, I will get x squared equal to 9. Take the square roots on both sides. Get absolute value of x equal to 3. So x is equal to positive 3, x is equal to negative 3. Those are the 2 bad points. And this is if you don't want to factor. But I always suggest you factor because it is going to help you in future steps. So what if I want to factor? I will say x squared minus 9 equal to 0. Then remember, we can write it as x squared plus 0x minus 9 equal to 0. So I need 2 numbers that multiplies to negative 9 adds to 0 because of the middle term's coefficient 0. So those numbers are negative 3 and positive 3. And I'm pretty much done with factoring. I say x squared minus 3x plus 3x minus 9 equal to 0. I factored out x from the first 2, get x minus 3. I factored out 3 from the next pair of terms, get x minus 3 as well. So I get x plus 3 times x minus 3. And hence, I solve for the bad points, and as you can see, I get the same answer. I get x equal to negative 3 and x equal to 3. So I need to discard these 2 points from the number 9. That's the way we will write the interval notation of the domain. So negative 3 is bad, 3 is bad, don't take either of them, and take everything else. So the domain, the first thing that we wanted to know is negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. Step number 2 is talk about the symmetry. To find the symmetry, I'm going to write down fx, which is your given function, and that function is x squared plus 4x minus 5 over x squared minus 9. And then you're going to find out f of negative x, which is equal to negative x to the power 2 plus 4 times negative x minus 5 over negative x to the power 2 minus 9. So I will get x squared minus 4x minus 5. So this minus doesn't change anything because you are squaring it. All over x squared minus 9. Again, the same thing. It didn't change anything. But see, this one is not equal to fx. As soon as you said f of negative x is not equal to f of x, I say it is not even or symmetric about y-axis. I have to check one other symmetry, and that is symmetry about the origin. So for that, f of negative x is good, but I need to know what is minus f of x. Minus f of x, as you recall from last class, you either multiply the minus to the top or to the bottom of the original function. I prefer the bottom, so I get x squared plus 4x minus 5 all over minus x squared plus 9. And this is not equal to f of negative x. So minus f of x is not also equal to f of negative x, so it is not odd. What does that mean? It means not symmetric about the origin as well. So there is no symmetry in this function, which is pretty usual. Number 3, we're going to talk about the x-intercept and the y-intercept. Well, for the x-intercept, I'm just going to set the rational function x squared plus 4x minus 5 over x squared minus 9 equal to 0. And I only care about the numerator, so I will say x squared plus 4x minus 5 equal to 0. You factor it. Again, my suggestion is always factor when you are doing rational functions. So I'm going to skip the process of factoring and go ahead and write the factors. X plus 5 times x minus 1 equal to 0. So the two solutions are x equal to negative 5 because of the x plus 5 and x equal to 1 because of x minus 1. Now remember the bad points? The bad points were negative 3 and 3. Those are the two bad points. So none of my solutions are bad because they're negative 5 and 1. They're not negative 3 and 3. So the x-intercepts are pretty simple to understand now. They will be negative 5 comma 0 and 1 comma 0. Well, how about y-intercept? The y-intercept is the other way around. You're going to set your x equal to 0. So you will say 0 squared plus 4 times 0 minus 5 all over 0 squared minus 9. And see, I get negative 5 over negative 9, which is a positive 5 over 9 by dividing. So the y-intercept is going to be 0 for x, 5 over 9 for y. Step number 4 is finding vertical asymptote. And I know the process. I'm going to first simplify the fraction. So we'll write fx equal to x squared plus 4x minus 5 over x squared minus 9. Remember, to simplify, I'm going to write them as linear factors. So we'll say x plus 5 times x minus 1. We know that we have already factored it. When we were trying to find the x-intercept, I already factored it here. So that's the beauty of factoring. I don't have to repeat that step. I did it for the bottom too. You know, it's x plus 3 times x minus 3. I was finding the bad points and I said, remember to factor. So when I factored them, I got those as well. So now, see, there is nothing in common between top and bottom. So there is no cancellation. And it is simplified. Because I cannot cancel anything, I'm just going to call that this is simplified. So what are the vertical asymptotes? Well, set the denominator equal to 0 now for the simplified form. And then you see the same two bad points, x equal to negative 3 and x equal to 3 are your vertical asymptotes. The only exception is I'm not going to write them as ordered pair, I'm going to write them as equation, just the way you see, and call them our vertical asymptotes. Step number 5 is finding horizontal asymptote, and that is to deal with the degrees. So degree of the top, as you can see, is 2, which is equal to 2 degree of the bottom. So degree of top and degree of the bottom are the same number. What does that mean? It means y equal to leading coefficient of top over leading coefficient of bottom is horizontal asymptote, which is going to be, well, if I think for the leading coefficient, both of them are 1.
So it's 1 over 1, which is 1. So I go ahead and say that y equal to 1 is horizontal asymptote. The next step is doing the number line test. So I will go ahead and do the number line test to understand the x-intercepts and the particle asymptote. So number line test. Remember your x-intercepts, if you go back, they are -5 and +1, whereas particle asymptotes are -3 and +3. And you need all 4 of them. So if this is 0, you will go 1, 2, 3, 4, 5. So that's -5. That's x-intercept. 1, 2, 3. That's -3 is your particle asymptote. So I will do the dotted line there. And then I go 1, 2, 3. X equal to 3 is one other particle asymptote. So gets a dotted line. And x equal to 1. 1 comma 0 is your x-intercept. So this is the point, and that is the point where the graph crosses the x-axis. Now at 0, the y-axis, I know the y-intercept as well. If I go back, the y-intercept is given by 0 comma 5 over 9. So it is less than 1, almost 1/2. So I will say here is the point 0 comma 5 over 9, and that's where the graph will cross the y-axis. Now what? Now I'm going to take a point both on left and right of each intercept and each asymptote, the vertical asymptote. So let's say if this is -5, I take -6. This point is going to work for both the right hand side of this point and the left hand side of this point. So let's call it -4. I want 1 on the left of -3. So I'll probably go ahead and say this is my testing point -2. Then 1 on the left hand side of +1, so let's call it 0.5. You want to be very close to 1. And then take between 1 and 3, so let's take 2 as a testing point. But again, see, 2 is on the right of 1 and left of 3. So that will work for both of these. And I need 1 more on the right of 3, so let's call it 4. And I'm going to test all these points on the given function. Which is my given function? Well, I know fx is equal to x squared plus 4x minus 5 over x squared minus 9. But as a matter of fact, it will be easier for you to calculate if you write it in the factored form. So again, factor it. So these were the factored forms, and I'm going to use this form instead. And what I do, write down each of the testing points. So -6, do f of -6. What does this mean? -6 plus 5 times -6 minus 1 over -6 plus 3 times -6 minus 3. And then you check the signs of each of these factors. So this one is negative, this one is also negative, over this one is negative, this one is also negative. So I have negative times negative positive on the top, negative times negative positive on the bottom, so the total sign is a positive sign. So I go ahead and say that -6 will be positive. Now I do the same work, but this time I do it for -4. So I'm finding f of -4. -4 plus 5, -4 minus 1 over -4 plus 3, and -4 minus 3. So I get this is positive, this one is negative, over this one is negative, this one is also negative. So see, on the top you have a minus now, but the bottom is plus. So total sign is a minus, which means I'm negative here. I do it for -2 now. For -2, you're going to input -2 in place of x in the factored form. So you get -2 plus 5, -2 minus 1 over -2 plus 3 times -2 minus 3. So this one here is positive, this one still is negative on the top, over, this one is positive, this one is negative. So I get positive essentially, but why I get positive, I get negative signs on both top and bottom. See, I get a negative here, I get a negative there, so together they will give you a positive sign. Hence, once I have this format, I will be able to say that at -2, my testing point, the sign is a positive. Then I'm going to go ahead and try to do it for 0.5. So for 0.5 being the testing point, I will get f of 0.5 because I'm replacing x by 0.5. You'll get 0.5 plus 2, 0.5 minus 1 over 0.5 plus 3 and 0.5 minus 3. So for this one, I see this sign is a positive, this sign is negative, this sign is positive, this sign is negative, just like the last one. So it remains negative over negative, hence positive. I have two more testing points. First, I'm going to go ahead and say that at 0.5, I am positive. And then I'm going to go ahead and test for 2 and 4. So let's do 2. So I'm finding f of -2, and I'm getting 2 plus 5 times 2 minus 1 over 2 plus 3 times 2 minus 3. So this is positive, this is positive, that is positive, that is negative. So you get positive on top, negative on bottom, total sign is a negative sign. So go ahead and say that at 2 you are negative. And finally, 4 is your last testing point. So you're finding f of 4. So you get 4 plus 5 times 4 minus 1 over 4 plus 3 times 4 minus 3. And as you probably have seen it already, all of the signs are pluses, both on top and bottom. So I get plus over plus, which is plus. And hence I get to say at 4, I am positive. The last information is step number 7, where you're going to draw the graph. So what I will do, I will go ahead and open a new page and kind of get all my information gathered when I'm drawing the graph on the last step. What information I need? I need x-intercept, y-intercept, number line behavior of signs, and vertical asymptote and horizontal asymptote. So -1, -2, -3. Remember, this is a vertical asymptote at x equal to -3. So write it down. -4, -5. This is a point where you will be crossing the graph of x-axis. The graph will cross x-axis. 1 is also a crossing point because it is an x-intercept. 2, 3 is a vertical asymptote. And this is x equal to 3, the vertical asymptote. And then I have y-intercept at 0,5 over 9. And I have at y equal to 1, the horizontal asymptote. If you recall, we found out the horizontal asymptote is at y equal to 1. We need that information too now. So this is say 1, and I do a dotted line there to understand the horizontal asymptote. And I try to recall the signs we got. So on the left of -5 you are positive, but on the right you are negative. So we'll go ahead and do these signs. -5 left you are positive, right you are negative. But the right of -3, if you recall the vertical asymptote -3, right you are positive. You're positive on the left of 1 as well. So I'll go ahead and get those signs. So you're positive here, you are positive here, the right of +1. And on the right of +1, you are negative, whereas on the right of 3, you are positive. So you are negative, positive. And let's try to draw the graph now. Remember, I'm crossing here. So as I get closer to the asymptote, I'm going to negative infinity because of this negative sign. And I will go up towards the horizontal asymptote, not cross it, stay under it. So that's the branch. What else we're going to get? On the right hand side of this vertical asymptote at -3, I will go to infinity. Why? Because the sign is positive. You will come down, cross the asymptote, horizontal asymptote at y equal to 1, cross the y-axis. Remember, this is the y-intercept, so I cross the y-axis. I'm still positive, but then at the point 1, 0, I'm going to cross. And as I get closer to the asymptote, x equal to 3, I go to negative infinity. Why? Because the sign is negative there. What else? On the right-hand side of this asymptote, I'm positive. So where will I find the graph? Because I'm positive, I'll go to infinity on the right-hand side for this asymptote. So that's the graph. And as I get closer to the horizontal asymptote in the long run, I'm getting closer and closer to the horizontal asymptote, never crossing, and that's the entire graph that you wanted to see. And that answers your question for drawing the graph of a rational function.